Welcome back, everyone. Now we come to the second session of the ISEG webinar series. I am Honghu Zhu of Nanjing University. I'm the Deputy Secretary General of ISEG. This afternoon, we will have 6 presentations. First, I would like to introduce the first one. Our first speaker for this section is Professor Devendra Narayan Sain. Professor Sain is the D.L. Shah Chair Professor for Innovation at the India Institute of Technology, Bombay, Department of Civil Engineering, Geotechnical Engineering Division. He is also the Vice President of ISEG for South Asia. He is also the Editor-in-Chief of Environmental Geotechnics. Today, his presentation title is Geomechanical Characteristics of Gas Hydrates Bearing Sediments. Let's welcome Professor Sain. Professor Sain, can you share your screen?
Is this okay?
Yeah, it's okay. Please start.
Thank you very much, Professor Zhu. Let me congratulate International Society of Environmental Geotechnology for this initiative. In particular, I would like to congratulate and thanks Professor Shibin and Professor C.S. Tang for putting in efforts in bringing out this series of webinars, which are basically dealing with the challenges and the opportunities. So I take this opportunity to share with all of you my initiatives in the field of energy geotechnics, geomechanical characteristics of gas hydrate bearing sediments. So this work has been done in collaboration with ONGC, Oil and Natural Gas Corporation of India. In the simplest possible form, this is a source of energy which we'd like to harness. And this is a big challenge to all technologists, administrators, and researchers. If you look at the world map, which is given by Collett et al. 2015, you will find that gas hydrates of methane type are available in several parts of the world. And that's the reason that the research has been focused in the recent past in harnessing the energy from them and to understand the geotechnical issues related to methane gas hydrates bearing sediments. I come from India, and if you look at the coastal margins of India, you will find that there are few locations where the gas hydrate samples have been recovered. I'll be talking about this subsequently. There are few other deposits along the Indian coast where gas hydrate occurrence has been inferred. So overall, this is becoming a very hot topic in India as well. And I was happy and lucky enough to be a part of the initiatives which were taken by our government and Oil and Natural Gas Corporation of India. As I said, methane gas hydrates are falling in the realm of energy geotechnics. The whole idea of exploration of reservoirs of gas hydrate sediments is to ultimately release methane gas, which is the source of energy. If you look at the structure, this is how the structure looks like of the hydrates. So in the water molecule, you have a CH4 molecule which is trapped. And the way we define this phenomena is it's a methane gas which is consisting of lattice of water. And in the hydrocarbon molecules are trapped and it resembles like a dirty ice. So I'll show you some of the pictures where you can appreciate it better. So the way to look at the gas hydrates would be that this is a multi-phase geomaterial. and of course resembling like ice-like clathrates. So their habitat, as we discussed just now, is mostly marine environment, and it is estimated that 1 meter cube of methane gas hydrate sediments would be able to dissipate 180 meter cube of methane gas at standard temperature and pressure. And hence you can realize that why everybody is interested in doing research in this area. So the research includes the exploration part of the hydrate bearing sediments, and then how to release the methane which is trapped in this cage of ice-like clathrates to use it in the energy form. This is how it looks like. There could be different sources of methane which might be trapped in these clathrates. So the way we define this is two broad categories: thermogenic. And thermogenic phenomena happens normally in the deep sea beds away from the continental shelf. And this mostly because of the chemical reactions which are going on in the Earth's crust. And this is where we can have gases like methane, we can have gases like ethane, and the gases like propane, which could be a consortium of the gases in which we are interested. The second category of hydrates is, which is the source is biogenic because of the microbial decomposition of organic matter in the environment, which is either lakes or offshore in the continental shelves and so on. And these are mostly methanogenic in nature. What are the challenges and where we can collaborate and where we can work together? And particularly those of you who are initiating your research in this area, the challenge number one is how to synthesize the hydrates in the laboratory. Because you must be realizing that once we talk about the source of methane gas, which is either thermogenic or biogenic, the question is how this gas migrates into the sediments. And this becomes a beautiful example of gas flows in saturated and unsaturated sediments. We require laboratory experimentation techniques. We require numerical modeling techniques to model these things. Another thing is, as I said, formation itself is a big question. So far, I have not been successful in synthesizing hydrates in my laboratory, which I was trying to do. So once you have synthesized the hydrates, then only we can talk about migration of gases and other geomechanical aspects associated with the hydrate bearing sediments. So when we talk about the hydrate formation, the morphology plays a very important role. And this is what everybody is trying to understand. What type of morphology is responsible for creation of a certain type of a hydrate bearing sediment, and how this morphology is going to influence the geomechanical properties. Now, when I say geomechanical properties, these are the elastic modulus, Poisson's ratio, shear modulus, bulk modulus, stress-strain relationships, permeability, coupled phenomena, which I'm going to talk about subsequently. This becomes a big challenge. Remember, the formation of hydrates is going to be under slightly abnormal temperature and pressure conditions. So the conditions required for formation of hydrate sediments would be extremely high pressures. It's expected because the location is somewhere in the seabed, and this temperature which are very close to 0 degree, 2 to 3 degree. So overall, this becomes a very complicated system. You remember in conventional soil mechanics, we used to talk about the grain structure of the soils. So this is where the morphology is going to control all the properties of the gas hydrate bearing sediments. We have three types of morphologies. One is pore filling. You can see now here the grains are getting filled up. The space between the grains is getting filled up by the hydrates. So this is the pore filling. We have load bearing, cementing sort of a thing, where the structure has a property to take the load also. And of course, the third one is the cementing, where the entire matrix gets cemented and it acts like a cemented sand. The biggest question is how to synthesize hydrates and how to detect what type of morphology is getting formed in these sediments. We are trying to do these type of studies, but still, I think a long way to go. There are many challenges. So laboratory simulation is a very big challenge in this context. And once you have synthesized this, then the oil industries are asking a question: how would you extract methane from the reservoirs which are rich in the hydrates? So I have shown here an animation. If I want to liberate energy coming out of the hydrate bearing sediments, what I have to do is I have to go for an exploration and drill a well. And this is the formation in which the gas hydrate bearing sediments are. We call them as hydrate bearing reservoirs, from where if I extract, methane gas will come out. So extraction is normally done by few techniques. And these techniques are either you depressurize it because the system is at a very high pressure, and because of very high low temperatures, the hydrates are getting interlocked in the sediments. So one of the techniques which is what is being mastered by everybody is depressurization by extraction well, and if I allow the suction to happen, or if I open it to the atmosphere. Thermal stimulation. If I heat up the entire system over here, all right, I can create a thermodynamically unstable situation which will allow migration of methane from these reservoirs. I wanted to simulate both these conditions in the laboratory, and this is where our efforts are on right now. Now, once you are extracting the methane gas from the hydrates, one has to be extremely careful, because there are several geomechanical mechanisms which are going to initiate the moment you start doing the extraction process. And this is where utmost care is required to understand the whole phenomena. And this phenomena is quite similar to the phenomena which you have studied in conventional geomechanics, where we were talking about subsidence due to excess withdrawal of water from the aquifers. Something of the same sort, where the stability becomes a big issue. I have tried to show it here in the animation form, and I will come back to this. So the first mechanism which is going to be very important is, if I am using the thermal stimulation, how heat would migrate into a multi-phase porous media like gas hydrate bearing sediments. Efforts have been done by people to study the heat migration in sediments. In fact, in our laboratory, my ex-students and present students are working in this area quite intensely, where we want to see how heat pulse migrates through the sediments and how it can be utilized for characterizing the geomaterials. The multiphase is basically methane and water. So think of a situation when you are puncturing the reservoirs, the gas is going to come out. This is how I have shown it in the animation. The gas will come out, and both have to be modeled. That means a multiphase system has to be modeled keeping in view that along with the gas, methane gas, the water is also going to flow out. So this becomes a coupled flow phenomena. What happens because of all these things is water is flowing out. Along with the water, the fines which are present in the sediments would also migrate. And I'm sure you are aware of the suffusion phenomena, where the migration of fine takes place, and because of that, the material loses its strength. Now, these things put together are becoming a big challenge on studying the well bore instability. That means once you lower down the well, and whatever infrastructure you are going to make, you will see in this cartoon, I will replay it, that the seabed subsidence is taking place because of extraction. And this seabed subsidence is something equivalent to subsidence of the geomaterials or of the bed because of discharge of water. And foundation instability is going to take place. The systems which are located on this type of formation, they may get unstable. Uncontrolled methane release is a very big issue, which is going to cause greenhouse effect. And sometimes you must have read in the literature that because of extraction of the methane, there is a possibility of triggering of tsunami. So this becomes a very interesting, very challenging topic for geotechnical engineers to study and to master. India has done a tremendous amount of work in this area, And Ministry of Petroleum and Natural Gas, Government of India, under Directorate General of Hydrocarbons, is very active in this studies. We have already gone for 3 National Gas Hydrate Program. We call them as NGHP1, NGHP2, and NGHP3. And these are in different parts and the locations of the areas or the bays where the hydrates have been identified. So KG is the KG Basin, Krishna Godavari Basin, Mahanadi Basin, and Andaman Basins. Interestingly, for a geotechnical engineer like me, an environmental geotechnologist like me, this becomes a very interesting case study where we have sands and clays both, which can be utilized for characterization and further studies related to the hydrates. So this becomes a very, very challenging situation. Now, I will come upon to the point that what are the pertinent questions in this subject and where the challenge lies and where is an opportunity to collaborate on the most challenging problems which the entire world is facing. So the pertinent questions are, what is the matrix of gas hydrate bearing sediment? What is it comprises of? So different phases, like when we talk about different phases, there are sediments, there are water phase, which is either unfrozen or frozen, and then there are gases which are interacting with each other. And what is the thermodynamic stability of these components when we talk about temperature and pressure relationships? So this parts also leads to the geomechanical properties of GHBS. That means this is what actually we are trying to study right now in our laboratory. How does shear strength, stiffness would vary during hydrate formation? So imagine the soil is getting frozen, the strength is increasing, the stiffness is increasing, but when I am trying to harness the energy out of these sediments, I am dissociating the sediments, and at that time there will be a drop in strength and stiffness. Now, if I do not know strength and stiffness drop, I cannot do the exploration properly. And then ultimately, what is the influence of the shear strength and stiffness of gas hydrate bearing sediments as far as the pressure and temperature phases are concerned? The multi-phase flow, which I just talked about, water and methane coming together during production, what would be their kinematics, how they are going to behave. We talk about relation of fluid permeability with respect to saturations of different phases. Now, when we talk about the saturation of phases, the most important saturation state we talk about is the hydrate saturation, because all these geomechanical properties are going to be a function of hydrate saturation. And hydrate saturation is an offshoot of the amount of initial moisture which is present in the matrix of the sediments, type of gases, concentration of the gases, and the thermodynamic conditions which are prevailing at that point, that is the pressure and temperature. How would you couple these things? So this becomes a very challenging thought. And then we want to talk about the production condition, that is wellbore design and efficient methane production. This is where the THM, that is thermo-hydromechanical modeling of gas hydrate bearing sediments, is required. Our group is working in this area. We are partially successful so far, but a lot is to be still done. There are some good success stories in the recent past. We have published extensively some papers, state of the art of gas hydrates and relative permeability of hydrate bearing sediments, formation and dissociation of methane gas hydrates in sediments, a critical review, and investigations on excess gas method. One of the methods to synthesize hydrates is excess gas method of methane gas hydrates. A comprehensive review on the geomechanical properties of gas hydrate bearing sediments. Our idea was to create empirical relationships which can be utilized to obtain elastic modulus, Poisson's ratio, shear modulus, and bulk modulus just by inputting the type of sediments which you are dealing with, the type of gas which you have, and what is the hydrate saturation. We have also done some work related to thermal instability of gas hydrate bearing sediments and what are the issues related to this. And another paper which we have published recently is investigations on gas permeability in porous media. So you must be realizing that at this point of time, all these studies appear to be slightly disjointed. But truly speaking, based on my earlier discussion, you must have realized that dealing with gas hydrate bearing sediments is not an easy task, because there are several mechanisms, processes, components which are involved which contribute to the overall material characteristics. So, what are my current focus research? Most of this part I have already discussed. I wanted to synthesize hydrates in my laboratory. It has not happened so far. And then once I have synthesized the hydrates, I would love to find out the gas permeability through the hydrates. It's something like when you do falling head test or constant head test, the same test if it is done on the frozen sediments, what the permeability would be. Having done this, the second aspect would be spatial distribution and quantification of the methane gas hydrates in sediment pores. Very tricky task. How would you look into the structure to say what type of formation has occurred? And then depressurization to release the methane gas. And once these two modules have been studied, we would like to study the shear strength and stiffness of the gas hydrate bearing sediments. So these are the two parts of the experimental study which we are doing. In the process, I have developed a excellent testing facility known as environmental or gas hydrate triaxial setup, which you can see over here. It has been recently installed and some of my students are working in this area. And then we have a laser microscope through which I wanted to see the spatial distribution of the hydrates which are getting formed and their morphology. Very ambitious project. And but then we have to challenge ourselves, if you really want to enhance the knowledge and the state of the knowledge. We developed high pressure hydrate cells to study these things. We are using time domain refractometry to establish the spatial distribution and to detect whether the hydrates are getting formed or not. And then we have also developed a temperature controlled direct shear apparatus, which happens to be, number one, very less expensive. You can do quickly tests, and then you can study very nicely how the gas hydrate bearing sediments of sandy type appears to be and what is their behavior. So right now our studies are mostly based on sands. Clays are still far away to achieve because of the nuances associated with the fine grained material, but we are sure that we will also study the sandy phases, clay phases. Whatever experiments we have done so far, we are trying to use them to do numerical studies. And this is where we use Tough Plus Hydrates software, which gives you the state of the material. This is a very rough idea on which we are working right now. We are trying to study what is multi-phase of the frozen sands. All right, so I started my research by considering how much fraction of the water gets frozen, how much water remains unfrozen, and then what's the interaction between these phases. So we have come out with these type of models where the gas hydrate bearing sediments have been defined in the 4 phases or a 3-phase system like your unsaturated soils, and then we are trying to come out with the empirical relationships. I hope you can realize that this is going to be a very intricate thing if I really want to look into the structure of the grains by using NMR, calorimetry, or the gas dialectometer. This is where we also use the concept of soil freezing characteristic curve. And some of my students are working in this area. Very simple looking experiments have been developed in my laboratory where I am freezing the sands and I'm seeing the dielectric response of these sands in a sample holder which acts like a capacitor, and then by using the bulk permittivity I am able to differentiate between the phases which are present in the sample. And fortunately this work has been published in Old Regions Science and Technology, a methodology to establish freezing characteristics of partially saturated sands. Now coming back to the mathematical modeling part where the challenges are. I have been talking about the pressure and temperature conditions. So this is a typical hydrate stability thermodynamic curve, all right, where you plot pressure and temperature on y and x axis. This is what is known as the stability curve. On the left hand side is the stability zone. Then we can show depressurization by this path. That means if I start from this point, the stability zone, and if I try to enhance the pressure, or if I do a reverse process, all right, then I can depressurize the whole system. I can do it by thermal stimulation also, enhancing the temperature. Sorry? Or the third one could be a combination of the two. All right, so these are the three techniques which we are trying to model right now, experimentally as well as mathematically. And this is the hydrate reservoir model which we have considered, where you have the seabed, overburden, top seal, bottom seal, and in between the hydrate bearing layers are entangled and followed by the underlying strata. So very quickly, I'll show you some of the results in which we were collaborating with our colleagues from China and Japan, and we have modeled the hydrate reservoirs from Nankai trough. Porosity logs have been created, hydrate saturation logs have been created, initial permeability logs have been created, absolute permeability logs have been created, and we know the properties of the sub layers which are present in the entire system. Now, this is how the well bore is being drilled and the heating is being done to liberate the gas. So these are the typical results which we were able to obtain so far. We have tried to model the gas production as a function of time. And this is what actually commercial agencies and the companies are interested in. They want to see how much gas can be liberated at the end of the day. So the whole purpose of doing this research is to give an answer to the government or to the industries who are dealing with alternate energy sources or non-conventional energy sources, a clear answer, what type of treatment should be done so that the gas can be liberated. And what would be the dynamics of this gas without causing any hazard associated with the instability of reservoirs. We have published these results in the journal Environmental Geotechnics along with Professor Lin Shen and Professor Feng. And there's a second paper which we have done for Shenhu, China case study, where also my collaborators have been Professor Shen and Professor Feng. So closing down to my discussion of today, what is the way forward and opportunities to collaborate? Because that is what actually is very, very important for all of us. You must have realized that this is a very complicated subject beyond the capabilities and capacities of individuals. But yes, our concepts are becoming clear by our studies and thoughts. I wish that investigation should be taken forward to study the suitability of the gas hydrate bearing sediments for carbon dioxide sequestration. Very important latest topic which everybody is talking about under carbon sequestration, and for enhanced methane recovery. I also proposed this through this forum that let's form a team of students and the postdoctoral students, and let's go for the exchange program to accelerate the knowledge which has been attained so far for the efficient utilization of the existing facilities. And this is where my concept of Sagarin, I would like to reiterate, becomes more, contemporary. So please be a part of this mission. And Sagarin, you can go on the website of the International Society for Environmental Geotechnology, and then you will find that this center has been publicized some time back. So let us collaborate and work together. Development of numerical simulators that would couple multi-phase fluid flow, non-isothermal heat transfer, and geomechanical properties of gas hydrate bearing sediments during hydrate formation and dissociation. So my request to all of you who have heard me is, let us initiate this collaboration as soon as possible. And of course, I always keep this quote in front of me: some journeys need no roads, only a willing heart. And there's another motivating quote which comes to my mind: what we observe is not nature itself, but nature exposed to our methods of questioning. And this was sent by Heisenberg and Fritz of Capra. This quotation is what says everything about the gas hydrate research. We are trying to model a phenomena which occurs in nature: methane gas getting trapped in the sediments under extreme pressure, low temperatures. And this is where, we have to simulate this mechanism in the laboratory and then go one step beyond this. Thank you very much for your attention. These are my associates who have taught me this subject so carefully and very well. Dr. Jeevan Joseph, Dr. Sanyam Dangayach, Lijit, who is still working with me, and he'll be finishing his PhD very soon. Very good postdoctoral candidate for those of you who want to hire him. Bhini Rani, who did MS by Research, and my another PhD scholar, Mr. Rao. So thank you very much for your kind attention. I'll be very happy to interact with those of you who are interested to teach me this subject, to collaborate with me, utilize my facilities. Please remain in touch, remain healthy and safe. Thank you very much.
Thank you, Professor DNS. The duration of your presentation is very accurate, half an hour. So thank you very much.
Thank you very much.
Yeah, I guess there must be a lot of questions from the audience, but due to the time limit, they can send you email, and you can communicate us through emails. Let's thank Professor Simon again for his wonderful presentation.
Thank you very much.
Thank you. Let's move on to the next presentation. Our next speaker is Professor Li Ming Hu. Professor Hu is a full professor at Tsinghua University School of Civil Engineering. He's also an ISEG Council member. Professor Hu's research interests mainly cover soil mechanics and environmental geotechnics. Today, his presentation title is Innovative Groundwater Remediation Technology. Let's welcome.
Thank you, Professor Zhu. And thank you, Professor Shi and Professor Tang, to invite me to give this webinar. My presentation is about the groundwater remediation technology. We are using a kind of a new technology called micro nanobubbles. Let's.
Yeah, please share your screen, Professor Hu.
Screen.
You can click the button, the arrow.
Yeah, but my computer asked me to. Okay. Can you see my?
Not yet.
Not yet. Okay.
Okay, wonderful. We can see your screen.
Okay. Okay, great. First of all, I thank my collaborators and the funding sources to support me doing this kind of research for almost 20 years. So my presentation is about. So first of all, I want to introduce the subsurface contamination in China and over the world, and then I talk about some technology for the groundwater remediation, and then I introduce the new technology. So as we know, the soil contamination is very severe in China and in some other parts of the world. So, since the economic development always causes the environmental pollution, and so actually the geoenvironmental engineering is starting from 1970s, and now it's very popular in China, since we have a lot of land and groundwater contaminated by all kinds of different kinds of contaminants chemicals. And also the groundwater has a lot of contamination. In China, 19% of urban aquifers are contaminated or exploited, and the U.S. FDA reports. So the groundwater contamination in U.S. I think it's become better, but in China, we are facing a very severe groundwater contamination problem. now over 75% of groundwater are not in good quality. And there are different kinds of chemicals in groundwater, such as VOCs, SVOCs, POPs, and metal, nitrate, arsenic. And this is contaminants of concern in superfront sites in US. So we can see there are different kinds of organics and inorganics in groundwater. So this is high arsenic groundwater distribution in China, and this is POPs in groundwater in China. We can see in the southeast of China, the economy is developed and the contamination is very severe. So the groundwater is contaminated, so we need to clean up the groundwater to keep the sustainable development. So it's a very, very challenging task for China. We can see from US EPA report, the superfront site, about 80% of the superfront sites need remediation or treatment, and about 80% of these sites, the groundwater is contaminated and needs remedies. So a lot of many kinds of groundwater remediation technology was developed in last 50, 60 years. It can be classified as monitored natural attenuation, ex situ, or in situ groundwater remediation technology. And the mechanism for the remediation technology is includes biological treatment, physical process, chemical reaction. I will introduce this later. So the MNA monitored natural attenuation just use the nature to clean up the contaminant. Is the remediation efficiency is very low and is time consuming, and this actually is not exactly technology. It's strongly depend on the site environment, since the MNA process needs suitable dissolved oxygen, the temperature, pH, and other geochemical conditions. For the ex situ groundwater remediation, the very popular one is pump and treat. That means we pump out the groundwater and treat it in the ground. So it's I think it's most used in all over the world. But for some cases, it's not work very well. For example, the contaminants with very high residual saturation, or contaminants with very high sorption capabilities, or in the very low permeability soils or aquifers, this technology is not working very good. And another problem is the tailing and the rebound effect. If we stopped pumping, the contaminant concentration will increase. That's because some contaminants are absorbed onto the soil particles, and if we stop pumping, the contaminant released to the groundwater again. So the contamination, the concentration will increase. And The in-situ groundwater remediation, that means we don't pump the water out and treat in the plant. We just treat it inside in situ. So enhanced bioremediation is a kind of in situ remediation technology. We need to have the specific microbe, and we need to improve the environment, such as providing nutrients and providing oxygen, and the microbe can grow and react with the contaminants. Another most widely used technology is in situ chemical oxidation. Especially in China, this kind of technology is very much used in the contaminant sites. So we use very strong oxidants to oxidize the chemicals. We can see this table. The oxidation potential, the higher the oxidation potential, the oxidation capability is much better. So we can use phantom and the pulse effect to act as oxidants. And some reports can use the ozone to oxidize chemicals. But as we know, the ozone is a kind of contaminant. If the ozone cannot be captured in groundwater and escaped from out of the groundwater, it can be a kind of a pollution. So it's not easy to control the ozone. So another technology is permeability reactive barrier. That means we can build up a wall, but this kind of wall is very permeable, and the contaminated groundwater flows through this wall and contact with the wall material, and the water can be cleaned up. The most used materials for this wall is the iron. We are very familiar with the iron, and to improve the efficiency of the iron with reaction with contaminants, some scholars developed the nanoparticle iron. It has a very high surface area and can absorb and react with the chemicals very efficiently, but it has some other negative impact, such as the aggregation of the nanoparticles and the remobilization of the nanoparticles. And actually, it's possible it can be a kind of a secondary contamination. We did some research on this. When the nanoparticle absorbed some ions, it can be it was charged, and the mobility of the nanoparticles which will be very much increased, and it can move with groundwater very fast. So that's kind of concern. This is our test result for the nanoparticles. It moves fast, even faster than the solute in the groundwater. And another technology for the VOCs is air sparging and soil whip extraction. It can be it can remove the volatile pollutants and increase the dissolved oxygen to increase bioremediation. But the problem is the zone of influence is very much small. So we need to build up a lot of injection well to inject the gas to remove the volatile pollutants. So as we see, the in situ technology is has a lot of advantages than the ex situ technology. So it meets the needs of the green and sustainable remediation. We can see from the US EPA report the in situ technology used much more in recent years. But in China, we still use in a lot of sites, we still use the pump and treat technology. As we just talked, the Can you see my screen?
Yes, I can see.
But I cannot see my screen.
What happened?
I don't know. Let me. Okay, can you see it?
Yes.
Okay. Oh, great. For the pump and treater, it's a long-term remediation process, and it has the tailing effect. For the bioremediation, we need to improve the site environment, and for the chemical reaction, it's always causes secondary pollution. It's not good. And for the SSVE, since the air injection is using the pipes, the bubble is very big and it cannot stay in the groundwater for a long time, and it cannot provide more dissolved oxygen for the groundwater. So in China, we are facing the problem that is we have the large contaminated area, and the contamination is very severe, and we have most of the sites include organics. So we try to develop a new kind of remediation technology to be used in the Chinese contaminated site. So this technology is micro nanobubbles enhanced groundwater remediation. So what is micro nanobubbles? It's ultra fine bubble. The diameter is less than 10 micron. So the micro nanobubbles has a very high efficiency in gas supply, since in the small bubbles the gas pressure is very high, so it can dissolve in water very easily, and it can stay in the water for a long time. So, and it can move with the ground flow, and it can has a very large zone of influence. This kind of technology can be combined with MNA, ICO, and pump and treat, and air spugging. And since we use the bubble gas as the reaction agent, so it can replace the chemical agents, and it can, if we use the air, oxygen, or ozone, it can improve the dissolved oxygen concentration, and it can enhance the bioremediation, and it can expand the zone of influence. and it's very easy to operate. So we did some basic research on micro nanobubbles. We can see even the microbubbles is no change of size distribution for very long time, for 2 days or even more. So it has a stable dispersion in water. Why is that? It's because the surface of the bubble has the negative charge, so it can keep the various stable dispersion. And we from the Young-Laffer equation we can calculate the internal pressure and the density of the bubble gas is very high, and also it has a very high surface area. It can very easily react with chemicals. As I just mentioned, the micro nanobubbles has the surface charge, so it can stay in water for a very long time. That means if we use some toxic gas in the micro nanobubbles and inject in the groundwater, it can stay in the groundwater and don't escape from the groundwater. So it has no secondary contamination. This is the model test for the micro nanobubble movement and permeability. So if the micro nanobubbles, the size less than the pore size of the soil, the permeability is not affected. And also we test the gas mass transfer rate. It's much faster than the ordinary small micro bubbles. This is test result for oxygen, and this is a test result for the ozone. As we know, the ozone it can self-degradation in a very short time. But if we use micro nanobubbles as ozone loader, the half-life time can be much increased from 0.7 minutes to the 10 minutes. So that means ozone can keep active for a very long time. And we use this ozone micro nanobubbles to react with different kind of organics. The result is very good. So we developed the field application scheme for different kind of contaminated sites. For the light contaminated site, we can use it as in situ or enhanced monitoring nature attenuation process. If it's for the severe contaminated site, we can combine with the pump and treat and aspersion technology to clean up the site very quickly. And also we did some physical model test to study the movement characteristics of the micro nanobubbles. This has some animation, but I cannot show it. We can see the oxygen nanobubbles migration in the soil model. So it can migrate very far. And this is groundwater remediation process. by ozone micronanobubble. The contaminant is methyl orange. Also, we use it in a site. The site is in Japan. It's TCE contaminated aquifer with at the depth of 12 meters to 16 meters. We use H2O2 combined with ozone nanobubbles to treat the groundwater inside, and we can see this is the well area for the site. We can see after 6 days treatment, all the contaminants are removed. Over 99% of contaminants was removed. It shows a very good effect. So we developed some theoretical model to simulate the whole process of the remediation process. As Persian and absorption model, and we can also include the phase between the free phase, among free phase, absorption phase, volatile phase, and dissolved phase, and react with chemicals or bacteria. Also, we can model bubble transport using the semi-chloride transport equations, and we can simulate the dissolved gas transport model using the similar model as the contaminant transport model. This is the equation for the model. I don't want to explain more. If you have any question, we can contact by email and discuss. And I'll just show you the result of the numerical model. This is simulation for the physical model test. I think they are agree very well each other. So let's come to the concluding remarks. Based on the research, the bubbles enhanced remediation technology has very high efficiency and is environmental friendly. We did some research work on the bubble properties. We know that the bubble can stay in groundwater for a very long time and has very rapid mass transfer, and it can very easily migrate in the porous media, and that means in the migration with the groundwater flow. And we did the field application work, and this site, the TCE contaminated site, was cleaned up in very short time. And we developed the theoretical model, and it can be, I think it can be a design or prediction tool for the remediation engineering, the site of remediation engineering. So I think we can try to use this kind of technology in China, and now we have a big project is the national key research and development project. We will use this technology in the chemical factory contaminated area, and I hope we can have a good result, and then we can communicate in the future. And I can show you some publications about this kind of technology and other research about the groundwater remediation by my group. And I hope you can have into it. And I'm glad to have your questions, answer your questions, and have your comments. Thank you very much.
Thank you, Professor Hu. Professor Hu just now gave us a comprehensive review of recent development of groundwater remediation technologies. Due to time constraint, if anyone wants to ask a question, he can contact Professor Hu directly after the webinar. Thank you, Professor Hu, again for your presentation. Now, let's move on to the next presentation: solid waste management, environmental engineering, and geoenvironmental engineering. Today, he will give a talk entitled Plastic Waste in Waste Disposal Sites and Their Re-Exposure and Release Potentials. Professor Fei, have you prepared?
Okay, so 30 minutes, 25 or 30 minutes?
30 minutes in total.
30 minutes, okay. All right, let me start. Well, first, thank you very much for joining the afternoon session. And this is obviously my pleasure to give a talk in this pretty important and well-recognized meeting, online meeting series. So my topic is plastic waste in waste disposal sites and their re-exposure and release potentials. Meaning, well, I'm going to talk about plastic waste and landfills, and not so much about the experimental results or mechanisms and reactions. I think this presentation I'm going to focus mainly on the background information and some of the common knowledges and maybe future directions. So it's I believe it's going to be a light presentation, and I hope you can enjoy some of the information I provided there. Oh, and I'm from Nanyang Technological University, NTU in Singapore. So all right, first let me talk about, well, two things I want to talk about as background information. The first is obviously the MSW generation, meaning municipal solid waste generation. I believe many people know what it is, and we are, as geoenvironmental researchers, we are very familiar with the MSW. But nevertheless, let me still talk about it for a while. MSW generation is a worldwide problem, as we can see, and we already know. Let me pull out this highlighter here. Because worldwide, all the countries are generating solid waste MSW, and then there are a few major solid waste management options that are used worldwide. So I will take three major countries and regions as an example. They are United States, China, and the European Union. So the first thing I want to point out is the amount of the solid waste generation per year. As we can see here, for US, China, and the European Union, the amount are more or less similar. Let me hide. Meaning other three regions generate on the order of hundreds million tons of municipal solid waste per year. The other thing I want to point out is the four major solid waste management options. Meaning in the different countries, they always rely on recycling, incineration, composting, and landfilling as the major disposal methods for municipal solid waste. Although the actual numbers are going to be different in the States, China, and the European Union. In the United States and European Union, we can imagine, they have strict policies and they have more advanced technologies. So more of the waste are actually incinerated or recycled, but still a significant amount of the waste is landfilled, as you can see here in the US, In the European Union, around 40%. In China, we have around 60% of the solid waste that are disposed of in so-called sanitary landfills, and around 8% of the waste goes to dump sites. These are less controlled landfills. So obviously, we know that solid waste generation is a problem we have to deal with. We have to solve this problem properly. And land disposal is a major method we rely on to treat solid waste now and also in the near future. And then still rely on the data from this water waste report that's generated by the United Nations, by the World Bank. I can further calculate something else. So by knowing the amount of the waste that's generated per capita in each country, and also their disposal methods, meaning how much waste is landfilled, we can calculate the so-called total MSW disposal worldwide in a year. And that number is going to be a very big number, 1.5 billion tons. That's just in 1 year, how much waste is disposed of inland, meaning using dump sites and landfills worldwide. We can also see that, the 3 major countries with the most waste landfilled are US, China, and India, but also many other countries that are marked in the red color and the yellow color. They indicate that these countries are disposing or landfilling waste on the order of tens of million tons. So overall, we know that worldwide, there are many land disposal sites, meaning landfills and dump sites, that are receiving continuously municipal solid waste from our cities and from our society, meaning solid waste disposal is a common practice, and then landfill sites, dump sites are almost omnipresent in the environment right now. For those landfill sites, I mentioned briefly before, many of these are so-called dump sites, meaning they are not properly controlled, or they don't have proper infrastructure to stop the waste from contaminating the environment. And these dumps, so I here take another screenshot from another recent report that is listed here. So this figure shows that many of the LMC, meaning low-income countries or low-medium-income countries and even upper-medium-income countries, are disposing of solid waste in the dump sites, not in the so-called controlled or sanitary landfills. So the dump sites, in the dump sites, the waste are not very properly controlled, as you can see in those photos below here, meaning people dump the waste, they throw the waste in there, and later on, all these wastes are very likely going to be re-enter or so-called re-exposed to the environment because of the poor engineered controls. Only in the high-income countries and parts of the upper middle-income countries, they can afford so-called proper landfills to contain and really isolate the waste from the environment. So here I just put another figure showing you a typical cross-sectional view of the landfills. This, I believe, all of us knows very well. These are ideal landfills that we throw the waste in, and then we can control them nicely. But just bear in mind that many times or many places in the world, the so-called ideal landfills do not exist, and then we are actually throwing waste into dump sites, which are not well controlled. So I'm going to skip this slide. Essentially, this slide, these 4 photos are showing some major big landfills inside or at the center of some modern cities. So just to summarize very quickly, what I have said so far is that we have to deal with the MSW problem, and then landfills and dump sites are the major methods we rely on to deal with, to dispose of solid waste these days. Another problem I'm going to talk about for a while is the plastic waste problem. I believe we all know that it's a very hot topic these days, and it's a pressing problem as we understand. First, I want to highlight to you that this special issue published by Science just 2 weeks ago, as you can see here on July the 2nd, 2021. This issue focused only or solely on the plastic problem called Our Plastic Dilemmas. So this Science issue is highlighting many things. Obviously, I'm only going to show you some things that are the most relevant to my talk today. So plastic problem we know is contaminating the whole environment is damaging this ocean environment especially, and then the plastics are actually coming from our daily activity. So to put it into a better perspective, let me show you this other figure. It's also from a science paper, but a few years ago. What I want to show you here is that, especially those two arrows below. So for the plastic problem, plastic waste problem, people first realize or notice this problem in the ocean environment. That is essentially showing, or this is the meaning of this arrow here. Sorry, the arrow below, the black arrow here, it says that the trends of plastic waste research starts in the ocean or in the marine environment, the aquatic environment, then gradually moves on to the so-called terrestrial environment, meaning in the soil and on land, where all these plastic wastes are generated. On the other hand, the flow of the plastic is actually from the land to the ocean, meaning from the human activities, from manufacturing, waste generation, waste disposal to the natural environment. But nevertheless, I think many of us have this feeling that we see so many different plastic waste and microplastic research papers these days. Most of them are focused on the marine environment, meaning freshwater, wastewater, maybe ecology, toxicology, and etc. Only a few papers talk about the plastic waste pollution, microplastic presence in the soil environment, terrestrial environment, or so-called in the solid waste related activities. But I believe this is going to be the trend, like is shown here, because we do have to understand where do all these plastic waste come from, how they are entering the environment, and etc. So that is kind of gradually getting into my point today, meaning we have to understand the plastic waste disposal, especially in landfills and dump sites. All right, move on to the next figure. This figure is taken actually from the very recent science issue, the special issue on the plastic waste problem. So what I want to just highlight, this is a
I'm sorry, Professor Fei, your PPT sharing is stopped.
At which slide? Anyway, I'm going to just continue with from the current slide.
Yes, please.
Later on I will send the PPT, but anyway, these are, some of them are just photos, So I'm going to move on to, right now I'm talking about this slide, background information or background knowledge about plastic waste. This is a busy figure. Essentially, it's taken from the science paper that's very recently published, 2021. It's a busy figure, but nevertheless, I'm going to just pick out a few things to discuss with you. Basically, this figure is showing the overall plastic waste flow in the world, meaning everywhere. But I circled here the focus of this talk today, meaning if you see the numbers here, these numbers are the amount of all the plastics that are ever made. And what we can see here is, there are around 2,000 million tons of plastic waste, plastic products that are still in use. How much plastic waste is actually generated and disposed? It's this number here, 4,000 million tons. So we can see that, the majority, actually the predominant amount of the plastic waste, plastic products that are generated are actually discarded and become waste. And they are primarily stored in landfills and dump sites, as indicated here. Later on, if you are interested, you can see the other numbers. But all these natural flows numbers, they are very, very small, although we talk about these a lot these days, right? The plastic waste that are flowing into the oceans, that are floating on the surface water, that are littered everywhere. These are, just on the order of a few million tons. On the other hand, we have around 4,000 million tons of plastic waste in landfills and dump sites. So that's where I think the two major points come together, meaning, well, first we are disposing, or we are landfilling waste, solid waste every day, everywhere. And then we are landfilling a major amount of plastic waste in the landfills and dump sites. Then my real question for the talk today is that, okay, what's going to happen to these plastic waste that are disposed of in landfills and dump sites. This figure is just basically summarizing what I have said before, but I do want to highlight this box one more time. This is essentially showing that, for all the plastics ever made, around 40% of them become plastic waste and they are disposed of in landfills. And then around 30% of them are disposed of in so-called dump sites, including some of the open burning of plastic waste. So that's why essentially landfills and dump sites are very critical in understanding and solving the plastic waste problems nowadays globally. This is just summarized as summarized here. Most plastic waste are disposed of in dump sites and landfills. So that's a major problem for us to understand and maybe to solve in the future. All right, so let me summarize again briefly. The objectives of this talk of the next 20 minutes is to assess and summarize the current knowledge of land-disposed plastic waste and microplastics. And especially my focus will be on three things: the quantity and the distribution of the plastic waste in the landfills, their long-term behaviors, that's a summary, and then I will try to assess, evaluate the re-exposure and release potentials of the plastic waste and microplastics to the environment from the land disposal site. All right, so so this is kind of a literature review, and I first start with the plastic waste disposal. Well, again, although it's called a literature review, but we did some extensive data analysis and calculations and figure making. So these figures, all the figures afterwards, are made by my team, and the tables are made by my team. So the paper is submitted. It's not published yet, but if you are interested, you can check the paper later. On this slide, what I'm showing is the trends of plastic waste generation and disposal in different countries and worldwide. So first, we see here, this is the trend worldwide. The black triangles here are showing how much plastic waste is generated every year from 1850s to 2020. The red triangles are showing how much of these plastic waste are landfilled cumulatively. We can see that this trend is kind of flattening out, which is primarily due to two things. One is the promoted recycling of the plastic waste, and then the other thing is the increased incineration rate or ratio of the plastic waste. Then we can break it down, or we can break these numbers down to see for different countries and regions how they are dealing with the plastic waste. In China, we can see a certain portion of the plastic waste is still being land disposed, as you can see here for the red triangles. It is very similar for the United States. We see that part of the plastic waste are recycled, but still much of it are still landfilled. The only region that is doing much better is actually the European Union. You can see that the amount of the cumulative, the cumulative amount of the, the annual amount of plastic waste disposal in the European Union remains stable for a long period of time. This is essentially because of their socioeconomic status and policy, meaning they emphasize and encourage a lot the plastic waste recycling and also incineration. So very little fresh and raw plastic waste enters the landfills. This figure to the right here is showing some other major countries in the world where we can find the plastic waste data and how do they do. So the major conclusion here we can make is that, for many of the developing countries, including China and Brazil, South Africa, India, and etc., Thailand, and maybe others, the amount of plastic waste that are entering the landfills and dump sites are still increasing every year. Meaning we are not only looking at how we can contain the plastic waste in landfills for the existing plastic waste. We also have to think about in the future, near future, how do we deal with the plastic waste safely in landfills and dump sites. So moving on, we know there are so much plastic waste in landfills and maybe microplastics in the landfills as well. What are going to happen to these plastic waste in the landfills? So we make this summary figure, two summary figures here to basically show you that these are the potential long-term processes or reactions that are going to happen to the plastic waste. I'm not going to describe all these reactions in much details and mechanisms, but I'm going to first read them all. The major reactions are going to be a bunch of different degradation processes: photo degradation, thermal degradation, and also catalytic degradation, leaching, and etc. Biodegradation as well. So all these are degradation processes that are going to happen to the plastic waste under landfill conditions. In addition, we also have mechanical wearing, meaning the damaging of the plastics by the forces, shear force, compression force, and etc. And then finally, we'll also have a pneumatic and hydrological transport of the plastic waste and microplastics from the waste to the environment potentially. Just remember that some of you may have noticed there are two very recent papers that are showing that microplastics have been found in landfill leachates. These are published, I believe, by He Pingjing, a very famous professor in Tongji University, and another paper is published by ECNU, Xie Bing in ECNU. So they are the first people that are reporting the detections of microplastics in landfill leachates, meaning that, you know, we store the plastic waste in landfills. We hope that they do not change at all. So they are not threatening the environment, but these are not the cases, meaning they will eventually break down to microplastics, and then they will be carried out by the leachate or maybe even by the wind and etc. to contaminate further the environment in the future. So there are quite a few things that are going on. We need to first understand what are the so-called long-term processes, and later on we can think about how to do the proper monitoring, mitigation, and engineered controls for the plastic waste and microplastic. Then move on to talk about the last part of the presentation today. We also summarize, well, basically we flip through maybe 200 to 300 different papers, and then we summarize so-called different re-exposure and release pathways for the plastic wastes and microplastics from the landfills. So let me also explain this a bit further, what we consider as re-exposure and release. Re-exposure is essentially the re-exposure of biogas, solid waste, and or leachate from the land disposal site. So because these waste, gas, or leachate, they contain plastic waste or microplastics, so they first of all, they have to be re-exposed to the environment. And then these re-exposed solid, liquid, and gas can carry microplastics and plastics to the environment by the next step, which is called actual release step of the plastic waste from the disposal sites. So again, I'm not going to explain all these details here. It's a pretty busy figure. Later on, if you are interested, you can check my slides and our paper. Basically, I just want to say that, you know, we summarize and we think there are the re-exposure of the plastic waste is very much site dependent, meaning that for the dump site, and dump sites meaning the not well-controlled landfills, and then the sanitary and well-controlled landfills, the re-exposure pathways are very different, and then also the probability of re-exposure of waste are very different. Then whenever the waste, the gas, or the leachate is re-exposed to the environment, they will carry plastic waste and microplastics to the environment. And then these releases are characterized into three major transport pathways, which are called manual pathway, waterborne pathway, and also airborne pathway. I will explain them in a bit more details later. So just remember that for a landfill, it's not 100% safe. And then even if it's safe for now, in the long term, it may fail. And later on, we'll talk about several potential failure mechanisms. And if it fails, it will release or it will re-expose the solid waste and leachate and gas to the environment. And then these solid leachate and gas, they will carry microplastics primarily to the environment. So basically, we hope the landfills are so-called permanent sinks or terminals for plastic waste and microplastics. But the reality is that, you know, in the long term, they are going to leak plastic waste and microplastics to the environment, meaning we do have to think more about how to permanently contain the plastic waste in the disposal sites instead of releasing them to the environment in the future. All right, so the next thing we've done in the review is actually to carry out a so-called level assessment for the re-exposure and release. This assessment, well, it's a risk assessment, so I believe many of you should be familiar with this approach, right? We first kind of qualify and semi-quantify how much, for example, how much waste can be released from a site at a certain time, and then how much of this site are vulnerable to the release in the long term, and etc. So we give them some levels and scores, and eventually if we combine the so-called probability versus the impact, we can come up with a risk level or a re-exposure level or re-exposure score. So the lower the score, the safer we are. The higher the score, meaning that it's very likely going to happen and it's going to have a major impact on the environment. So I took another screenshot for this big table. In this table, essentially what we've done is to summarize the literature, as you can see here. For example, for the downside exposure, we've gone through many literatures and we try to look for the numbers, especially the percentage numbers, meaning that we will see, for example, one study is saying that around 50% of the dump sites are going to leak solid waste to the environment in the next 5 years, or and etc. So we look for all these percentage numbers and then we summarize as much as we can in this table here. Also, I'm not going to tell you all the details, but this is basically the methodology we are using to use to look for different good studies and then put their numbers and pull out their numbers to come up with the probability of the waste re-exposure. Similarly, we can also summarize the impact of each re-exposure. And then as you can see here, we have all the references and etc. So then by multiplying the probability by the impact, we can come up with a re-exposure score or re-exposure level, as you can see here. And then we have from very low to very high 5 different levels. But obviously, I'm not going to read the big table because it's going to be very tedious and time-consuming. I'm only going to show you some of the major results here. So for the re-exposure assessment, here we look into different re-exposure pathways that are only applicable to dump sites. Some of them are applicable to both the dump sites and landfills, for example, slope failure, waste mining, coastal erosion, flooding, and etc. Then we did all these probability multiplied by impact analysis and come up with re-exposure levels. So what are the results? We can see here that dump sites are very obviously the most important or the most likely pathways to re-expose the waste, liquid, and gas that's containing plastic waste to the environment. So they have very high scores for all these categories. For the others, for example, slope failure, waste mining, and etc. And then also in the next slide, I'm showing more of the other types of landfill failures. But for these cases, mostly, the level or the score is not very high, meaning they are not very likely going to release a huge amount of plastic waste and microplastics to the environment. The other two things that we need to keep in mind are contaminant leakage and leachate collection from the sanitary landfills. They are going to transport a significant amount of microplastics from the disposal sites, from the landfills, to the other environments. So just to summarize the re-exposure levels here, dump site disposal, contaminant leakage, and leachate collections are going to be the major re-exposure pathways. Now we move on to talk about the last part of my talk today, is the release pathways of the plastics waste and microplastics. I'm going to skip this, this slide, which shows the methodology again, but it's very similar. It's a semi-quantitative risk assessment approach. So what we did, again, is very similar. We first know that the waste is exposed. Then we want to see the exposed waste, how does the exposed waste transport to the environment, meaning they are transported manually by scavenging and recycling, by waste mining and treatment, and also they can be transported by the natural forces, meaning the waterborne pathways and airborne pathways. So among all these pathways, and after all the assessments and analysis, what we can see here is that, for the plastic waste, the most likely release pathways are scavenging from the dump sites. This is, I think, very easy to imagine. And also mining of the dump sites and landfills, meaning displace the plastic waste to other places for further treatment. These are essentially the two dominant pathways for the plastic waste, meaning the big pieces of the plastics to leave the landfills and dump sites. For microplastics, we have quite a few different pathways. So I'm going to just read them quickly here. Scavenging, waste mining, leachate leakage, and also leachate treatment. These are the dominant pathways for microplastics to leave the disposal sites. The next slide is not showing much, meaning all the airborne pathways are going to just contribute minimally to the environmental release of microplastics and plastics. All right, just to summarize, quickly summarize what I have talked about here. Again, this is a pretty high-level introductory and qualitative analysis of the plastic waste and landfills. So I briefly talk about what are the potential long-term processes that are going to happen in the landfills to plastic waste. And then we list all the re-exposure and release pathways and then assess their probabilities, meaning how likely are they going to be a critical issue. So later on, what can we do? We can obviously think about the in situ monitoring, the lab tests, the full-scale mitigations, and even the policy makings that are targeting to reduce the threats of the plastic waste and microplastics to the environment. So that's pretty much it. The last thing I do want to highlight, although I'm not going to talk in details, is that in the paper we talk more. Obviously, we summarize all these the reports from actual sites, and then we did all these statistical analysis, and then we plot all these. But again, because of the time limitation, I'm not going to talk about these. Again, if you're interested, please keep an eye on this paper. This review paper is under review now, and we hope it's going to be finalized soon. Again, if you're interested, please check with me later, or you can check the Google Scholar. Thank you for your attention today.
Thank you, Professor Fei. Your presentation is very interesting and very informative. Due to time limit, let's move on to the next presentation. Stabilization and solidification of hazardous waste, CO2 sequestration and utilization. He has served as an associate editor for soil use and management and editorial board for Journal of Hazardous Materials. Today, his presentation title is Low Carbon Stabilization and Solidification of Contaminated Sediment. Let's welcome Professor Wang.
Thanks, Professor Zhang. Thanks for your kind introduction. Can you see my screen?
Yeah, perfect. Yes.
Okay, thank you. My name is Lei Wang from the Technical University Dresden. It's my great honor to attend this online conference. First of all, I need to thank Professor Shi, Professor Tang, Professor Shen, and other colleagues for your kind organization and invitation. And I also want to thank everyone for attending my presentation. Today, I will introduce the low carbon stabilization solidification of contaminated sediment. With the development of the Chinese economy, nowadays China has many world-class container ports such as Shanghai, Shenzhen, Ningbo, Hong Kong. Today I will select the case in Hong Kong because I studied my PhD in Hong Kong, has some experience about the sediment treatment. To maintain the sufficient depth of the shipping line, the sediment, especially in the container ports, should be judged annually. And due to the marine activities, such sediment is usually contaminated. So before disposal or before recycling, it should be treated. In Hong Kong, from this table, we can find that the judged sediment, the amount of judged sediment increased every year. And in 2016, the judged sediment exceeds 10 million cubic meter, and about 1/3 are contaminated sediment. The sediment has high content of organic matter, about 6.9%. It also was contaminated by the heavy metals such as zinc, copper. So the sediment should be treated. The conventional method for the sediment remediation, just the disposal of sediment in the mud pits, and the sediment transported to the mud pits and will cover with clean sand. But this method will easily lead to the secondary pollution due to the nearby marine activities. So it needs long-term monitoring. For example, in Hong Kong, the contaminated sediment mud pits located near the Hong Kong airport. With the development of the Hong Kong airport, the sediment should be judged and transported to other places. So the Hong Kong government want to design some method to treat such contaminated sediment. We select the solidification and the stabilization method. We try to mix with sediment with some binder to recycle the contaminated sediment into useful construction materials, such as load bed materials. It can be used for the construction materials and with low environmental impacts. This is judged marine sediment. This sediment with high clay content. If we use this sediment for the construction materials, it will lead to low strength due to the high content of clay compared to the natural aggregate. And also, the organic matter in the sediment will delay the sediment hydration, lead to low compressive strength. Such high content of heavy metals also will influence the sediment hydration, lead to the low property of the final product. In our previous study, we tried to add some filler and fibers to reinforce the skeleton of the structure. It can increase the compressive strength by 3 times. And also, we use some thermal treatment, alkaline extraction, to remove the organic matters to improve the property. It also very useful, but this method will increase the time, increase the economic costs. So we try to find some sustainable materials to treat this contaminated sediment. In this case, we use some industrial waste, such as low calcium waste, like fly ash, incinerator, sewage sludge ash. It contains high content of silica oxide, may facilitate the pozzolanic reaction, and generate some CSH to further improve the property of the sediment blocks. Also, we also add some calcium-rich materials such as GGBS and the calcium carbide residues to provide the hydraulic reaction to improve the performance of the final products. So this is a judged sediment. We can add a little bit cement and add the aggregate to reinforce the structure, and add some industrial waste to partially replace cement, combine them together to produce the sediment blocks. We also use CO2 curing to improve the reaction of the sediment blocks. So in Hong Kong, if we want to recycle this contaminated sediment into paving blocks, firstly, it needs to pass the TCLP requirement, and then it should provide the high compressive strength. For the paving block for pedestrian use, the compressive strength should be higher than 30 MPa. For vehicle use, the strength should be higher than 45 MPa. This is the experiment procedure. We use the dry mix method, use the pressure to produce the sediment blocks, use air curing and CO2 curing. We also test the mechanical strength, leachability of the final products, and use the microstructure analysis, mineralogical analysis to explain the SS mechanisms. In this study, we select the contaminated marine sediment, select the binder to aggregate ratio at 1.3, water to binder ratio at 0.28. This is very low water to cement ratio. This is the reference product. We use 25% cement and the 75% aggregate. The aggregate contains the sediment. It shows the high compressive strength meets the requirement. With the addition of some industrial waste to partially replace cement at the dosage of 20%, it will slightly reduce the compressive strength, but also can improve the water resistance. These materials still fulfill the requirement. Among these four materials, we find some calcium-rich materials like GGBS, CCR. It can provide a relatively high strength at 7 days because the hydraulic reaction is relatively fast. By comparison, the low calcium material with high silica content, it shows low strength development. Because the pozzolanic reaction is relatively slow, we use the QXRD to quantify the compounds in the final product. After 28 days air curing, we can find that there are some similar content of CSH gel in the PFA and the GGBS added materials. So these materials show the comparable compressive strength to the OPC samples. But from this figure, we also find that there's more than 30% unreacted cement in this system. So in the marine sediment, the OPC with air curing is not very effective because the organic matter and heavy metals will delay the hydration process. So we want to use CO2 curing to facilitate the reaction. CO2 curing was also called accelerated carbonation. This is natural carbonation. It's relatively slow, near more than 1 year. The degree of carbonation may be still very light. But accelerated carbonation, we use the high concentration of CO2. It will carbonate these materials in a very short time. But the moisture content is very important. If we use high moisture content in the system, the high moisture content will hand the CO2 diffusion lead to low degree of carbonation. But if there's no water or very limited water, it also will delay the carbonation, also will delay the further hydration of the cement-based product, because cement is essential for the hydration. So we adjust the moisture content in the mixture, and we also find that with the high moisture content, the carbonation is very slow, and if we adjust reduce the moisture content, it will accelerate the carbonation, and usually it will release largest heat in 1 hour. And too much water in the system, the humidity in the cooling chamber is relatively high. It's not very suitable for the carbonation. From this, the compressive stress, we can find that this is one-day air cooling. This is one-day CO2 cooling. CO2 cooling is very effective for enhancing the early strength. But high moisture content, it result a low degree of carbonation and result in the low compressive strength. This is spin-off sealing test. We can find this air cooling. After CO2 cooling, the color turns into colorless. It means most of calcium hydroxide in the system was carbonated into the calcium carbonate. And at a moisture content of 3.3% is optimal moisture content. It can provide favorable carbonation and also provide the favorable hydration of the cement-based product. After CO2 cooling, if we add the additional air cooling, it can further improve the strength due to the continued carbonation and the rehydration. From TGA result, we can find that after one-day CO2 cooling, most of the calcium hydroxide will turn into the calcium carbonate, and the calcium silicate will turn into the CSH gels. After 7-day air cooling, further carbonation and cement hydration occurred. So the new peaks of the calcium hydroxide appeared in this curve. Then we use the CO2 cooling for the waste incorporated system. If we incorporate some calcium-rich materials, it can sequestrate a lot of CO2 in the system. But the silica-rich materials is not very effective because during carbonation, some calcium will react. So with insufficient calcium in the system, it cannot activate the PFA and the ISSA for the pozzolanic reaction. So CO2 cooling is very suitable for the calcium-rich system. In this system, we can find, especially for the GGBS, lot of calcium hydroxide turn into the calcium carbonate. But the pozzolanic reaction was delayed. And after the CO2 cooling, we detect the TCLP leachability of the sediment blocks. We can find the calcium-rich materials can reduce the leachability of toxic element because it can increase the pH of this system, reduce the leachability, because most of toxic element in alkaline condition has low solubility. CO2 cooling will slightly reduce the pH, so result in the increase of the leachability, but it is still acceptable. So in this system, we use some green materials combined with CO2 curing to recycle the sediment into eco-friendly paving blocks. To further improve the property and reduce the carbon footprint, we use some magnesium oxide cement, MgO, to partially replace the OPC. Because OPC is a commonly used material with high mechanical strength, but also have associated with high carbon emission, we want to use the magnesium cement. This cement with high compatibility with some impurities because it can provide sufficient hydroxide, and this cement during production has low energy consumption, and during the curing it can absorb a lot of CO2 in the system. But it also has some disadvantage such as low water resistant, low compressive strength. So we want to combine them together to utilize the advantages, overcome the individual drawbacks. This is binary cement system. If we increase the content of magnesium oxide, the leachability of toxic element significantly reduced because it can provide sufficient hydroxide, increase the pH, so it can enhance the immobilization of this toxic element. But the hydration product, the magnesium hydroxide, is relatively weak, so the strength reduced gradually. From the XRD result, we can find the addition of MOC will generate the large amount of magnesium hydroxide. And after 28 days air curing, more than 40% cement unreact. So we also want to use CO2 curing to facilitate the reaction process. After 1 day CO2 curing, the strength increased to 2.84 volt, and additional air curing, we can find it can improve the strength, especially with additional air curing and additional moisturizing. And after 7 days, additional 7 days curing, the strength can as higher as more than 45 MPa. It can meet the requirement of paving block for vehicles. Accelerate carbonation, the magnesium oxide turn into magnesium hydroxide and magnesium carbonate, and the cement also can be carbonated. And we can find after additional 7 day air curing in the July system, the samples can be continually carbonated, a lot of calcium carbonate, but the color still into colorless, means very few amount of calcium hydroxide or magnesium hydroxide. But in the wet system, the rehydration occurred. Some surface turn into slightly pink color. Also, the TGA result shows that after CO2 curing, more hydration and hydrolate and carbonates are produced, and additional air curing can further increase the hydration product and the carbonation product. From the MIP result, we can find that after CO2 curing, the porosity of the product reduced, especially after additional air curing in the wet conditions. The CO2 curing can fill the capillary pores, and additional air curing can further improve the mesopores. And we use the CO2 curing for this binary system. this is 0% MOC means pure OPC system. This 100% MOC means pure MOC system. We can find both CO2 cooling can benefit the strength improvement in all the samples, but CO2 cooling is very effective for these materials, binary system, with 20% MOC to 60% MOC. So the binary system is during CO2 cooling is very suitable. From the TJ result, we can find the greater proportion of carbonates and hydrates in the binary cement system, because the MgO in the binary system can provide the nucleation site to improve the carbonation. Also, we can find from SEM image, we can find there is a positive relationship between oxygen and the carbon, and there is high concentrate of magnesia, there is low concentrate of calcium. It means it generates the magnesia calcite in the system during the carbonation of this binary system. And we also conduct the TCLP test, find the MgO addition can significantly reduce the leachability of most heavy metals, and the CO2 cooling just slightly influences the immobilization efficiency. So because the MgO can provide sufficient hydroxide, so it has large buffering capacity for the pH change. So the binary cement system and the CO2 cooling also very effective for the stabilization or solidification of this contaminated sediment. Lastly, I will quickly introduce some other case. We also recycle the sediment into different sediment product. If the strength, we use large content of sediment, it shows relatively low strength, but it can be used as fill material. It has medium strength, larger than 7 MPa in compressive strength. It can be used as partition block. If the strength is higher than 30 MPa, it can be used as paving blocks. We also detect the mechanical strength, leachability test, conduct the cost and the benefit assessment. And we find the recycled sediment into the paving block is optimal scenario, because this one is the most profitable option. Also, in order to overcome the drawbacks of low water resistance of MgO system, we add some silica-rich materials, because we want to combine them together to generate the magnesia silica hydrolate. This is very stable materials. It can improve the mechanical strength and the water resistance of sediment blocks. Also, if the sediment has highly contaminated by the arsenic, the OPC system may be not very efficient. So we add additional calcium-rich materials to provide a stable calcium arsenic complex to enhance the immobilization. Also, incorporation of red mud promotes the iron arsenic complexion to reduce the leachability of arsenic. For some sediment with high content of organic contaminants such as PAH, PCBs, so the cement is not very efficient. So we add some biochar to benefit the immobilization of such organic contaminants. So biochar also can has a beneficial effect on the cement hydration during the internal curing effect. So biochar immobilizing contaminants and promote the environmental acceptance. The way forward, we also want to reuse power plant fuel gas or cement plant fuel gas for the CO2 curing of sediment blocks. And we also want to use low carbon cement or carbon negative cementitious materials to produce the sediment blocks. Also, we want to enhance the functional property of sediment blocks to enhance the value of the final products. So that's all. This is my presentation. Thank you.
Thank you, Dr. Wang. Your presentation is very interesting, and now the Chinese government care very a lot about the low carbon problem. So I think your research works will be very helpful for building environmental friendly environment. Thank you.
Thank you. Thank you. Thank you.
Thank you very much for all the participants in this section. For tomorrow, we will have another 2 sessions. We would like to see you tomorrow morning at 9 o'clock. Thank you all. Bye-bye.